All right, Chapter 11, Section 2. We've talked about the two types of energy, kinetic and potential. Today we're going to talk about the conservation of those two. So first thing you need to know is the law of conservation of energy. Much like the law of conservation of momentum, we're talking about saving what we have. So we're in a closed, isolated system here, so energy cannot be created and it cannot be destroyed, but it's conserved. And it can actually change types of energy. So it can go from kinetic energy to potential, potential energy to kinetic. It can also go between different types such as thermal to chemical, chemical back to thermal. It can also go into mechanical energy, which is the general term for kinetic and potential energy when we put them together. So the entire system, if you think about an object sitting on a shelf, it has a potential energy because it's just sitting there. But as that object gets knocked off the shelf and is falling toward the earth, that number for potential energy is changing from potential into kinetic. So at that last moment before it reaches the ground, that is when all of the potential energy, has transferred or transformed into kinetic energy. And we're going to call mechanical energy ME. Okay, so again, what you have to start with is what you have to end up with, much like with momentum. So the way that we look at mechanical energy is ME equals KE plus PE. Okay, and the way that this works out is if you have an object sitting, it's all potential. There's 0 for KE. If an object is right before it hits the ground, then it's all kinetic and 0 potential energy. Okay, so it's kind of this fluctuating system, but you don't gain or lose anything from it. So conservation of mechanical energy, one way that we can look at it is, again, what you start with is what you have to end up with. So your initial kinetic and your initial potential has to equal your final kinetic and your final potential. So let's go ahead and look at an example of how you can work this out. Your example for today is you have a 22 kilogram tree limb. It is currently 13.3 meters above the ground. But during a hurricane, it falls on a roof that's 6.0 meters above the ground. So the first thing that we're going to solve for is to find the kinetic energy of the limb when it reaches that roof. So we're going to assume that for this problem, the air resistance is negligible. That it does not exist for this because we don't want to try to calculate in for friction for this course. So what we're going to start with is potential energy. We need to know what we had initially and what we have currently as it reaches the roof. Because if you'll notice in our equation or in our given information, we do not have a velocity. So we actually cannot use the kinetic energy formula. But remember what I just said. What you have in potential and kinetic kind of changes and shifts as it moves from a higher location to a lower location. Okay, so PE, let's go ahead and solve for what it is when it's at the roof level. So 22 times 9.8 times 6, you should get roughly 1,293.6 joules. So this is when it's at the roof. Okay, now we need to figure out what it is for initially. So 22 times 9.8 times 13.3. So 2,867.48. You could have also plugged this in as just 13.3 minus 6, and that would give you the change in potential energy. So looking at the change in potential energy here, you should roughly get about 1,573.88 joules. Okay, and that should be about right. There might be some differences based on where you have rounded numbers, but as long as you get close decimal-wise to this number, that's correct. So that's finding the kinetic energy when you have information that doesn't necessarily apply to the kinetic energy formula. But once you find all of this information, we can always go back and apply what we knew from previous chapters, like chapter 2, 3, and 4. So in the rest of this example, same information, we found the kinetic energy, but now I want to know what is the speed of the limb as it reaches the roof. Okay, so what do you know velocity is for a tree limb that is just hanging out in the tree? It's not moving, right? It has all potential. So initial velocity is 0. We're trying to find final velocity. We can figure out the distance that it is from where the tree limb is to where it reaches when it reaches the roof. And we know what acceleration due to gravity is. So we're going to use the VF squared formula. VF squared equals VI squared plus 2AX. And just go ahead and plug in. We have 0 squared for VI, so that kind of goes away. We have 2 times 9.8 multiplied by whatever the difference is between 13.3 and 6. So when you go ahead and plug that in, you do have to take the square root of that final number because we're not looking for VF squared, we're looking for VF. And when you find VF, you should roughly get about 11.96 meters per second. Okay. There are some practice problems I want you to try. Page 730, this is number 16 through 20. So go ahead and add those to your notes, and this is the end of section 2.